sixth lecture. This lecture is sponsored by Department of Civil Engineering, IIT Madras, GCRF, Clean Environment and Planetary Health in Asia, CEPHA Network, and Air Quality Management Association. Go to the next slide. So basically, we started this lecture in October 2020. It's more than 2 years now. The idea is to, under 5 verticals, engagement of citizens, networking with research and students, empowering the stakeholders, and innovative solutions and knowledge exchange. So all these 5 verticals are the key aspects which were considered in this interactions. Next. Go to the next. So within the CEPHA, we started several activities. We also come out with a newsletter, then documentary, which tells how solid waste can be managed. It's particularly for the school children. There are several community activities we have conducted to engage the citizens, several panel discussions, workshops and symposium, and also, of course, research engagement. Next. So a couple of months back, we also started to take this air quality management lecture series to the next level. We also started an air quality management association, basically to enhance the understanding of science behind the air quality by promoting knowledge on clean air and understanding best working practices. And our director, Professor Kamakuti, inaugurated this in presence of the former chairman of Tamil Nadu Pollution Control Board. Next. Of course, we are having a conference on 7th Indian International Conference on Air Quality Management, IACAQM 2022, which focus on measurements, modeling, health risk, and public policy. The conference will be held from 29th November to 1st December 2022 at IIT Madras. As a part of this conference, we are also conducting a winter school on source apportionment, modeling, and health risk assessment from 27th November to 1st December 2022. So this will be supported by various research institutes, academic institutes, and including the Bath University with Professor Richard Ball. Next. So this air quality management lecture series is a first of its kind in India, basically to give as a platform for the young researchers, scientists, engineers, and educators to understand the challenges, key issues, innovative solutions to address the various issues on our air quality management. Next. So these are all eminent speakers who gave the talk. Next. Next. Yeah. So the last talk was given by Professor Virendra Sethi, IIT Bombay, and today's talk will be given by Dr. Richard Ball from Department of Architecture and Civil Engineering, University of Bath, UK. I request Gopika to introduce Richard Ball, and then Richard Ball will give the talk. Thank you, Professor Richard, and thank you all for joining this talk. Gopika, please introduce.
Good afternoon, everyone. It is my great pleasure to introduce the speaker of the day, Dr. Richard Ball. He is a reader in the Department of Architecture and Civil Engineering at University of Bath. He graduated from University of Bath with Bachelor of Engineering in Material Science and Engineering. Later completed his PhD in Material Science, also at Bath. He has published over 100 papers in referred international journals covering batteries, fuel cells, solar cells, ceramics, composites, NDT, sensors, sustainable construction materials, and air quality. Recent research has focused on the development of novel coatings for buildings to help improve air quality and the study of air quality in refugee camps around them. He is a chartered engineer, method scientist, and a fellow of the Institute of Materials, Minerals and Mines. The talk for today is titled Mitigating the Effects of Air Pollutants on People and Buildings, which will cover the influence of poor air quality on both people and buildings, as well as modern repair solutions for indoors and outdoors. So we extend a hearty welcome to you. Please share your screen for the talk.
Yeah, Richard, you can go ahead and share the screen.
Okay. Okay, so can you see that one okay?
Yes, we can see.
Okay, right. So Gupika, thank you very much for the introduction. It's a great pleasure to be invited to give this talk. I guess can everybody hear me okay?
Yes.
Okay. So as Gupika said, my talk's about air pollutants, and I'm going to be talking a little bit about the effect on people and buildings. See if I can get that to go. So in particular, I'll be talking about pollution and damage to limestone buildings. So we've got a lot of limestone in the UK. I'm going to be introducing a product called NanoLime, which can be used for consolidating stone. And then I'll be talking about photocatalytic materials and coatings that can be used in buildings. And then finally, if we've got time, I'll show you a few slides on some work that we did looking at air pollution in refugee shelters. So I'm from the southwest of England, and the red circle that you can see on the map, that shows roughly where Bath is. Actually, it's probably slightly to the left of that dot. So that's where I'm located, and I work at the University of Bath. So that's an aerial picture of Bath. You can see it's up on top of the hill. The city of Bath is down the hill to the right-hand side of the picture. You can't quite see it there. So we've got probably a smallish campus compared to some of the bigger institutions in India. But it's a nice place to be, and it's a nice surrounding area. And this is the city of Bath. So you can see Bath Abbey in the bottom right-hand side of that image, and you can see that a lot of the buildings in Bath are made from Bath stone, which is an oolitic limestone. And this is the Roman bath. So Bath is very famous for the Roman bath. It's a World Heritage City, and it's a tourist attraction. And these are the Roman baths. You can't bathe in the water anymore, but there's a hot spring underneath the city that feeds this pool, and the Romans would go and they would enjoy the hot water, and think that they can benefit from the minerals in the water as well. So this is a photograph of Bath that was taken in 1952, and you can see that compared to what the city looks like today, it was a lot dirtier. There was a lot of smog and smoke from coal burning, and this type of pollution, it would have had an effect on people, and it also has an effect on buildings. And we still see today that pollution can affect buildings in Bath. This is a photograph of some terraced houses in the city of Bath, and what you'll notice is that they're different colours. So on the left-hand side, we've got a building that's looking particularly dark, black, and then in the middle, we've got one which is quite nice. So this is a natural colour of Bath stone, and then on the right-hand side, we've got one which is brown. So what's the story behind these buildings? Well, occasionally building owners decide that they want to have their building cleaned. So various processes are used for cleaning the stone, and when they're cleaned, they look quite nice and fresh and new, but shortly afterwards, they will start to discolor again. So the building on the left hasn't been cleaned, the building in the middle has been cleaned, and the building on the right has been cleaned, but the photograph was taken a couple of years after it's been cleaned, and you can see that it's starting to turn brown again. This is a picture of a statue from Brompton Cemetery in London, and this shows a very similar effect to what we saw with the Bath stone. You can see that there are the black deposits on the surface of the stone, and these are generally made up from gypsum, that's calcium sulfate, and particulates such as carbon particulates from exhausts. And you can see, first of all, the top of the head is badly eroded, so we can see that the stone is much smoother. You can't see the finer detail so well. And also there are white streaks going down the front of the face, and this is because the gypsum is very slightly soluble in water, and when it rains, the rain runs off down the places where it's white and it removes the black deposits, whereas where the rain doesn't run, the black remains. So in terms of what's actually happening, we're reacting with the surface of the stone, and then we're washing off those reaction products. So we're going to get degradation and erosion of the surface of the stone where it looks white, whereas where it's black, you could perhaps argue that it's stable. So in terms of whether we should be cleaning buildings or not, we might clean them and they might look nice, but the consequence of that is that if during the cleaning process, we're removing the surface, and then if that degradation, if those reaction products build up again, then slowly we're eroding the surface of the building through the cleaning process. One of the ways that we can study the rate of reaction on the surface of stone, and also lots of other materials, so if you want to look at corrosion of metals as well, is to use a microbalance. And this is a photograph of a microbalance. So on the right hand side, you can see a little balance at the top, and there are two wires that come down. And if you look on the right hand side, then there's a little pan. So in that pan, you would put a counterweight. On the left hand side, there would be a much longer wire that runs down a tube, and you would have a piece of stone on a similar pan in that longer tube, and you can pass different gases through that tube and then study the increase in weight of your test sample under different atmospheric conditions. So this was work that was done at Bristol University. So I used to work at Bristol University in the early 2000s, and the study was looking at the effect of pollutants on Bath stone, and the two pollutants that were being investigated were sulfur dioxide and nitrogen dioxide. So the experiment was done where the weight gain was measured over about 25, just under 25 days, for 5 parts per million SO2, 10 parts per million NO2, and then a mixture of a combination of the two gases, which was 10 parts per million NO2 and 5 parts per million SO2. So what can we see from these results? Well, we get a weight gain with the SO2 and the NO2 on their own. But when we have those two gases mixed together as a combination, the weight gain is much higher. It's much higher than it would be if we just looked at the individual weight gains. So if we have a mixture of these acidic gases, then the reaction on the stone is accelerated. This is actually because the NO2 will oxidize the SO2 to SO3, and then when it reacts with water, it forms sulfuric acid rather than sulfurous acid, which is what forms with SO2, and that's a more reactive gas. So if we can, it's important to reduce pollution, and it's important to try and reduce a whole range of different pollutant gases as much as we can because of these effects of them working together. So here we can see a photograph of Salisbury Cathedral, and again this is made of a limestone similar to Bath stone. I'm not sure if it is exactly Bath stone, but about 10 years ago some conservation work was going on to replace some of the stones that were badly weathered and affected by pollution in the city. And you can see the chapter house. So the chapter house is this big room off the side of the cathedral. And you can also see a photograph of some of the stones that have been replaced. So this slide here shows some of the types of damage that you might expect to see on the surface of stone when it's weathered and when it's exposed to pollution. The photograph on the top left-hand side, you can quite clearly see, if you look at that corbel, you can see a crust, and that's a gypsum crust that's formed as a result of reaction with sulfur dioxide. There can also be deposits of calcium carbonate formed through precipitation on the surface of the stone. And what tends to happen is when the stone weathers, the underlying stone weathers faster than the crust. So you end up with friable material and a layer of crust. And what we were doing in Salisbury is they were replacing a lot of these corbel stones. So you can see one of the replacement carvings on the bottom left and a couple of the quite badly weathered stones in the middle and on the top right. So what we were able to do is to experiment on these stones using different techniques. So in this case, we were looking at nanolime in order to understand what the effect of that process is and whether the nanolime was able to actually consolidate the stone effectively or not. So we used it as an experimental building. So to introduce nanolime, lime is the term that's used to describe calcium-based chemicals, like it could be used to describe the oxide or the hydroxide. In this case, we're using it to describe calcium hydroxide. And nanolime is a product that was produced in Italy to consolidate fresco paintings. And probably about 10 years ago, a number of companies started importing it into the UK and marketing it as a consolidant for stone. So these types of buildings that we see where pollution has affected the outside and the stone is becoming friable, they would be marketing it as a treatment in order to stabilize the surface of that stone. So nanolime actually consists of nano-sized calcium hydroxide crystals, which are naturally hexagonal in shape. So you can see the TM image on the right, and they're actually in a suspension of alcohol for a number of reasons. So this could be ethanol or isopropanol, and the suspension is added to the surface of the stone, and it will soak into the stone. So this plot here shows some mercury intrusion porosimetry results to show the pore structure of a number of different stones. We've got two stones. We've got a Bath stone and a Chilmark stone, and we've got weathered and non-weathered examples of this. So what we can see is that if we compare the weathered and the non-weathered stone, the Chilmark stone has got much higher volume of pores, around 10,000 nanometers, compared to the non-weathered stone. So weathering of Chilmark stone tends to increase the size of the pores. If we look at the Bath stone, then we have non-weathered, which is red, we have weathered, which is green, and we have the weathered crust, which is dark blue. So you can see that the dark blue thick line has quite a low porosity. So Bath stone is a stone that will naturally form a crust on the outside. So some stones form a crust, some stones don't. Bath stone is a stone that happens to form a crust. So we can treat the stone with nanolime, and these are some scanning electron images which show what the surface of weathered and non-weathered chill mark stone looks like before and after treatment. And you can see that after the stone's been treated with the nanolime, it does have a certain effect of blocking some of the pores on the surface, which we wouldn't want to block them all because we want the stone to remain breathable. But you can see that there is a physical effect of applying nanolime onto the surface of the stone. We analysed the effect of the nanolime using two techniques. We used a Carsten tube, which is a tube that's filled with water. It's attached to the surface of the stone, and then the rate at which the water soaks into the stone is measured, and this gives an indication of the reaction on the surface of the stone and whether the pores on the surface of the stone have been blocked by the weathering process. And the drilling resistance drills a hole into the stone at constant rotational speed of the drill bit, and at the same time it can control the penetration rate and measure the load, so the force pushing back on the drill bit. So if we look at some results from the Carsten tube first, we can see that the gradient of the line relates to how fast the water can absorb into the surface of the stone. So the steeper the gradient, the faster the water absorption. So we can see that by treating with nanolime, we have a shallower gradient, which means that the water takes longer to soak in. So this shows us that we're blocking the pores. If we look at the drilling resistance result, so this is a close-up of one of the holes we drilled into a corbel. So we tested the corbels before and after treatment. We can see this is an example just to give you an idea of what sort of data we can get from drilling resistance. So we've got the drilling resistance plots on the top of the slide and a polished cross-section of the stone at the bottom. And if we look at the polished cross-section, we can see the gypsum crust on the surface of the stone. It's a slightly denser layer. And then if we compare non-weathered and weathered stone, on the top, the drilling resistance plot, we can see that the weathered stone has got a much higher drilling resistance over the first 2 or 3 millimeters of depth. So it goes up to 15 or 20 newtons compared to just under 5 newtons for the non-weathered stone. So you can see that the drilling resistance machine is very sensitive at measuring the presence of a crust, and also gives us an indication of the mechanical properties of the stone, so how hard it is to drill into. So these are some of the results from treating limestone with nanolime. The grey line is the drilling resistance before treatment, and the black line is after treatment, and the red shading is the increase in the drilling resistance. So we can see that at different lengths of time, 20 days, 30 days, and 6 months, for the non-weathered stone, we see an almost immediate benefit from treating with nanolime after 20 days, and the drilling resistance is increased. And we can see that the depth of the nanolime has gone in about 10 to 15 millimeters into the surface of the stone. If we compare that to weathered stone, so this, remember, this is Bath stone, so it's got a crust on it. So we can see that it takes longer for the nanolime to go in through the surface crust, and we have to wait about 6 months for it to carbonate to actually see that increase in mechanical properties. But these results show that using nanolime can help consolidate the surface of the stone. So another strategy that we might want to use to try and improve air quality in the built environment is to use photocatalytic coatings. So photocatalytic coatings have been used in buildings for quite a time. On this slide, we can see the Jubilee Church in Rome. So this is a concrete structure which has got the surface, has got titanium dioxide on the surface. The photograph on the left with the man standing in front shows a wall, and half the wall has been treated with titanium dioxide. And you can see that the half that's been treated is much whiter than the uncoated half. So TiO2 can have a self-cleaning effect. So it will react with pollutants and degrade them. And that's what's happening on this wall. So any products that will soil the surface of the wall are being broken down by the titanium dioxide, washed off in the rain, and therefore keeping that nice white appearance. The photograph on the bottom left are some paving slabs which are produced by the Mitsubishi Corporation. So they're from Japan, and they're coated with titanium dioxide, and the idea is that they help to remove nitrogen dioxide from the air around busy roads. So I think they're marketed called Noxia paving. And then we've got some pictures of a white cement that's been treated with TiO2, and we can see the surface of these materials, as you can see in the SEM picture on the bottom right, are quite porous. So any photocatalytic material that's going to work, what we're looking for is a high surface area. So how does a photocatalyst work? Well, titanium dioxide is a semiconductor, which means it's got a band gap, and when it's irradiated with light, electrons will gain energy, and then an electron will go from the valence band to the conduction band and produce an electron-hole pair. And those electrons and holes can take part in photoreduction and photooxidation reactions. So what they can do is react with oxygen and with hydroxide or water to produce a superoxide anion and hydroxyl radicals. So in this diagram on the left-hand side, we can see how we might make a photocatalytic coating. We have our substrate material, and we will stick our particle of titanium dioxide onto the surface, and then we will produce these radicals on the surface of the TiO2, and then any pollutants such as volatile organic compounds, pathogens, or pollutants such as oxides of nitrogen that are absorbed on the surface of the TiO2 will then be broken down by those radicals into carbon dioxide, water, and nitrate. In the case of VOCs, if they're large VOCs, they might be broken down into intermediates in the process. So one of the key things about titanium dioxide is that this process works because the light is being absorbed. And it just so happens that titanium dioxide absorbs light below about 400 nanometers, which is in the UV range of the electromagnetic spectrum. So the intensity of UV from the sun is much lower than the intensity from the visible wavelengths of light. So we can see that the plot on the right hand side shows the spectrum of light from the sun, and the absorption band for the absorption of TiO2 is shown. So you can see that line going across the top, and then around just before 400 nanometers it moves down. So if we wanted to make titanium dioxide more effective in the built environment, what we want to do is absorb more of the light which is visible. So we want to absorb more of the higher wavelengths of light, and we could do that by trying to shift that absorption edge to the right hand side on the plot. So that's shown by that blue arrow. So we want to move that absorption in the right hand side and make more use of those higher wavelengths of light. So one of the ways that we can do that is to try and treat the titanium dioxide in some way, and we could do that by doping it. So we can dope it with metals such as cobalt and tungsten, and we can also try incorporating materials such as graphene into the titanium dioxide, which can also help improve the photocatalytic performance. So in order to manufacture titanium dioxide, we can make it through a hydrolysis reaction by reacting titanium propoxide with water in an acidic environment, and that will produce titanium dioxide nanoparticles. And if we add cobalt chloride or some tungstenic acid to it, then we can incorporate that into the titanium dioxide. And we can see the reaction, the apparatus on the right hand side. You simply do it in a round bottom flask and control the temperature. So it's done at about 80 degrees centigrade. So the equipment you need, it isn't particularly expensive or complicated. So we looked at a number of different elements for doping. We looked at cobalt, and one of the materials that's used quite a lot indoors is coated medium density fiberboard. So you can see the picture at the bottom right hand side is some coated fiberboard, and then on the left hand side we've got lime render, and we were looking at incorporating these titanium dioxide particles into both of these products. And we also looked at coating aluminium oxide with cobalt doped TiO2. So aluminium oxide is used as an additive to the resins that are used to produce the coatings on MDF board in order to make it harder wearing. So we used a rig to look at the reaction with NOx, and we can see some of the results here. So we did some tests under UV light and under white light. So if you look at the plot on the left hand side, we can see that the best performing material is a degusser P25. So P25 is a standard anatase titanium dioxide, so you can just go out and buy that in the shops, and it's got a high surface area and it's very effective under UV light. But you can see that if we look on the right hand side, this is a similar test that was done under white light, and we can see that this time the two best performing materials are the orange and the green line, which correspond to the aluminium oxide coated with titanium dioxide doped with cobalt. And this is outperforming the P25, and also the surface area of these homemade particles is slightly larger than the P25. So we could think that the effectiveness of these particles is slightly better than we see on here if we took into account the proportionally lower surface area. So this really illustrates how doping can improve the performance under white light. We also looked at doping with tungsten, and we looked at the effect of the amount of tungsten that was added to the titanium dioxide. We added 1, 2.5 and 3%, and you can see the nanoparticles that we manufactured. There are some SEM images on the left and some transmission electron images on the right, showing that we have got nanoparticles there. And we looked at, first of all, the degradation of methylene blue. So this is looking at how well it can degrade a dye in an aqueous environment. And we can see that they outperform the P25. So the P25 is green. And we can see that as we increase the amount of tungsten, we appear to increase the performance. So the 3% in the water is giving the best performance in terms of the degradation. We also looked at the degradation of NO2 or NOx, and again we can see that the 3% is working very well and outperforming the P25. And then finally we looked at using dyes which can be painted on the surface of materials. So we treated some MDF, so we produced a titanium coated MDF material, which you can see some little squares of that in the bottom right hand side image, and we used 3 different dyes which are commercially available for testing the activity of photocatalytic materials. So the company is called Ink Intelligent, and they produce 3 dyes which they call an explorer, a visualizer, and a validator. So we drew lines of each of these inks on the surface of our material. We covered half with aluminium foil, and then we exposed that to light, and then the inks change color if they're reactive, so we could compare different concentrations of tungsten in the TiO2 for the coatings and see which ones are reactive. And we can see if we compare the results, then we can see that the P25 is working, so that's quite active. We can see that under white light, the 1% and the 3% tungsten doped TiO2 products that we made are also active. We can see that the brown line on the right hand side is disappearing at the top where it's been exposed. If we look at the UV, then we can see that some of the bluer and purple dyes are changing color as well. So it seems to be slightly more effective under UV when we have it on the surface of a material like that. But they are all showing a photocatalytic effect. We also looked at the effect of graphene. So these are some of our materials which contain a combination of titanium dioxide and graphene. So we had 2 different materials that we were testing. One that was mixed mechanically, and one that was mixed where the graphene was actually added to the reaction vessel during the sol gel reaction when we were making the titanium dioxide particles. So you could say that the one where the graphene was mixed in is perhaps more intimately mixed than the one that was mixed mechanically, where the graphene was just added afterwards. So you can almost see the graphene sheets in the bottom left hand, the bottom middle image, and you can also see the sheets of graphene in the mechanically mixed one in the transmission electron image, which is shown as the top row. So this worked very well. In fact, the product the one that we made where we mixed the graphene in with the sol gel reaction, so the intimately mixed one gave the best performance, which is the green line at the bottom. So our graphene titanium dioxide material worked well, and the graphene was enhancing the effect of the titanium dioxide, and we think that this is because it was increasing the recombination time. So if you remember back when we form the electron hole pair, sometimes the electron can drop back and it can recombine with the hole. And in the presence of graphene, the electron can go out onto the surface of the graphene, and this means it's harder for that recombination process to take place. We also did some tests looking at whether we could use the graphene titanium dioxide as a detector for oxides of nitrogen. And we did this with some colleagues at the University of Messina in Italy, and we took some interdigitated electrodes, which are shown on the left-hand side of the diagram in orange, and a very thin layer of our graphene titanium dioxide was put onto the surface of those electrodes. And then the electrical properties were measured under exposure of NOx. And what we found was that we were able to degrade and detect the presence of NO2. So these are some of the results. So on the bottom left, you can see the interdigitated electrodes, which is the little sort of square bit. So you can see the material coated on the surface of those. And then on the right-hand side, we can see some various graphs that show the change in resistance under different concentrations of NO2. And we can see that under very, very low concentrations in the parts per million and parts per billion range, we see a change in the resistance. So this is a very, very sensitive detector. And we can see that the response of the S1, which is a sol gel, one where the graphene was mixed with the sol gel, that gives the biggest response. So in our previous experiment, we saw that that was best at degrading the NO2, and in our sensor experiment, we can see that that's the most sensitive one to use as a sensor. And when we plot the response, the ratio of the resistance to the measured resistance against log of the concentration, we get linear relationship. So we've got a nice relationship if we want to use this as a detector. So bringing the two together, I've explained about nanoline and also described some of the experiments that we've done with titanium dioxide. So we thought that it would be interesting to look at the effect of treating bath stone with a combination of nanoline and titanium dioxide. So we took small centimeters cubes of bath stone, so you can see a picture of one of those on the bottom right hand side of the image, and we put them into a glass reaction vessel, which you can see on the top right hand side. And then each of our samples was exposed to a different gas. So you can see in the table, we exposed to 7 parts per million NO2, 7 parts per million SO2, a combination of 3.5 parts per million NO2 and SO2. And for each of those gas combinations, we looked at an untreated stone, a stone that was treated with nanoline, and a stone that was treated with photocatalytic nanoline, which is a nanoline with titanium dioxide. And we undertook these tests under visible light, and then we also did a repeat test with the 7 parts per million SO2 under UV light. So these are some SEM images of the surface of the stone. So we can see the stone in its natural state on the left-hand side, the nanoline treated stone in the middle, and the nanoline TiO2 stone on the right. We can see that the treated stones look very similar. They've got a fine texture and some larger pores on the surface. So what we wanted to do was try and understand what was happening on the surface of these stones when we put them into the environment with the NO2 and the SO2. Is there anything actually happening on the surface? And the technique that we used to try and determine that was X-ray photoelectron spectroscopy. So XPS produces a spectrum, which is the count, which is a signal against binding energy, and each element will have a specific binding energy. So we can see this is a typical survey spectrum from XPS from the surface of our treated stone. So you can see all the elements there that you would expect to see. So we've got peaks for calcium, oxygen, titanium, carbon, and sulfur. But XPS is very clever because the position of these peaks relates to the chemical state of the element. So we can tell the chemistry around that particular element. So these are the results that we got. And I don't normally like putting tables up because there's lots of numbers. But in this case, what you can see is that we've got the binding energy for our different elements. So we've got carbon, nitrogen, oxygen, sulfur, calcium, and titanium. And we can see that the binding energies stay pretty constant. So if we look, for example, at oxygen, we can see that we've got a binding energy around 531, which is for the oxygen in the calcium carbonate. And then where we've got a photocatalytic nanoline, we saw a slightly lower binding energy for oxygen, and that was the titanium dioxide which was that's the oxygen that's incorporated into the titanium dioxide. So using this technique, we can differentiate between oxygen in carbonate and oxygen in an oxide. What's interesting is if we look at the results from the sulfur, and if you look at the sulfur binding energies, you'll see that we've got SO3 and SO4, and the binding energies for SO3 are around 167 to 168, whereas we see that we've got one binding energy that stands out, which is 169.4. So we've got higher binding energy, and this binding energy corresponds to sulfate. So this is telling us that we're forming calcium sulfite on most of our samples, but our sample at the bottom, where we've got that higher binding energy, we're forming calcium sulfate. So something is happening for that last sample. So that last sample happens to be our photocatalytic nanolime exposed to SO2 under UV light. So only when we've got titanium dioxide in UV light do we see sulfate. Otherwise, we see sulfite. So what's happening? Well, these are some of the reactions that we can use to explain. So what's happening is that SO2 reacts with water to produce sulfuric acid. That sulfuric acid will react with the calcium carbonate or the calcium hydroxide in the nanolime to produce calcium sulfite. And then on an actual building, eventually that calcium sulfite would oxidize and it would produce calcium sulfate. So if we look at the surface of buildings, we always see sulfate. We don't really see sulfite. So the sulfite's something that is perhaps could be described as an intermediate. When we have titanium dioxide in UV light, we're producing the radicals on the surface, and those radicals, such as the hydroxyl radical, can then oxidize the SO2 to SO3. So we oxidize sulfur dioxide to sulfur trioxide, and then our SO3 will react with water to produce H2SO4, which is sulfuric acid. Now, sulfuric acid is a much stronger acid than sulfurous acid, and the sulfuric acid can then react with lime or calcium carbonate to form calcium sulfate. So what's happening is the presence of the titanium dioxide is accelerating the reaction of the SO2, and it's going to react with any lime-based material that's on the surface. So if we add nanolime to the surface of the stone with titanium dioxide, we're probably promoting the reaction of the pollutants with the nanolime, because the nanolime is calcium hydroxide, whereas the stone is calcium carbonate. So initially, before the nanolime is carbonated, it's more likely to react with pollutants. So we could perhaps use this sort of material as a sacrificial layer as well on the surface of buildings to absorb and react with some of these pollutants, taking them out of the atmosphere. So I've got some conclusions here. I won't bother to go through these. We could apply nanolime. We could also have a lime render on the surface of a building. So lots of buildings have a lime mortar, which is used as a render. So I've talked a bit about indoor air quality. Now I'm going to talk about, I talked about outdoor air quality. Now I'm going to talk about indoor air quality. And in the Western world, we spend about 80 to 90% of our lives indoors. And also in a lot of buildings, in order to try and make them energy efficient, they're made airtight, and that means that the air exchanges are lower, so the risks of pollutants building up inside buildings is higher. And in a lot of airtight buildings, occupants complain about poor air quality. And there are lots of articles in the press regularly about the effects of poor indoor air quality. So we've got some here. We've got formaldehyde in new buildings related to the building boom in China. We've got bottom left hand one about airtight modern homes. We have an article about pollution in cities during COVID from people using their boilers to heat their homes more, which were putting out more pollutants. One at the bottom middle about pollution from kitchens, so and kitchen cleaners and cooking and things like that. We have an article in the top right. So this was a school that had some building work done, and they used a foam building product that was releasing formaldehyde, and the levels were so high that they had to close the school. So lots of examples of poor indoor air quality causing problems, and these problems are commonly associated with sick building syndrome, which is something that's used to describe sickness that people feel when they're exposed to a poor internal environment. So one of the studies that we did was to look at how some of the products that we might use indoors can absorb and desorb commonly used pollutants that you might find inside your home. So we looked at 4 different materials. We looked at an uncoated medium density fiberboard, a coated medium density fiberboard, a lime-based material, and sheep's wool. And each of these materials has got different surface properties, so we can see different porosities on the surface, different surface areas, and also different chemistry on the surface as well. And these were tested in an environmental setup at the Building Research Establishment. So we can see a rough layout of what the rig looked like. We had a clean air generator, which was used to produce clean air, which was then humidified. And then that clean air was then doped with various volatile organic compounds and formaldehyde, and then passed through a chamber. And you can see that the circuit on the bottom carries dopant air into the chamber, and we also have a pipe at the top which is labelled clean air, so we can pass either clean or doped air over the surface of our samples. And you can see in the bottom of this slide the cylindrical chambers which were used to hold the samples, so it was possible to run about 5 tests in parallel. And sampling was done using 10x tubes at the end. So 10x tubes are absorbent tubes. You absorb the VOCs onto the tube, and then you use a GCMS to analyze the pollutants on the tube in the end. So we looked at 4 different pollutants. We looked at formaldehyde, toluene, limonene, and dodecane. So we've got different size organic compounds, and we've also got a polar organic compound, which was the formaldehyde. So the experiment was carried out by firstly passing clean air through the chamber to condition the samples, and that's not shown in this plot. And then the polluted air, so the doped air, was then passed into the chamber, and then after a certain period of time, clean air was passed through the chamber. So a typical result is shown by the red line on that graph. So you can see we get an increase and then a drop off. So what's actually happening? Well, when we introduce our doped air, some of that doped air, some of the pollutants in that air are being absorbed onto the surface of our sample. And that means that we measure a lower concentration. However, as the surface of the material gets saturated, it will eventually reach an equilibrium where the concentration is constant. So when this concentration is constant, it's that horizontal line at the top, that shows that the material cannot absorb any more of those VOCs. Then when we switch on to the clean air, we see a drop in the concentration of the VOCs, but there is some desorption occurring. So even when we're passing clean air into the chamber, some of those VOCs are coming off of the surface of the material, and there we can continue to measure them. So we can see that there's absorption at the beginning and a desorption at the end of the experiment. So these are some of the results. So you can see that each of the different pollutants is shown on a different plot, and each plot contains the 4 different materials, including the reference chamber. So there are a few things that we can draw out of these plots. The first one is that the lime material is got a very high surface area and a good capacity for absorbing dodecane and also limonene and formaldehyde. So we can see that it's the concentration of these pollutants doesn't get up as high as some of the other materials. So lime is quite good at regulating the concentration of these. If we have a lot of lime inside, then it's going to absorb them, but equally you can see that they are deabsorbed as well. But we could regulate the concentration perhaps and stop concentration spikes. The other thing which is interesting to look at is the effect of sheep's wool, and sheep's wool is the red dots, and particularly in the case of formaldehyde. So formaldehyde will react with organic material and it will react permanently, and we can see this as the absorption of formaldehyde on the sheep's wool is quite effective, so the concentration never gets up as high as in the reference chamber because it's reacting on the surface of the sheep's wool. But there's no desorption of formaldehyde when we switch onto the clean gas. So that means that all the formaldehyde has been completely locked up in the sheep's wool. So sheep's wool is commonly used as an insulation. It's seen as a green, perhaps greener alternative to using mineral wool or some of the inorganic insulations. So there could be capacity to use sheep's wool as a sink to absorb pollutants such as formaldehyde in an indoor environment, perhaps by passing some of the gas from the room, the air from the room over the sheep's wool and letting it take out some of these pollutants. So finally, we're reaching the end part of my presentation. So recently we had a project looking at air quality in refugee shelters, and there's obviously a lot of refugee camps around the world, and air quality can be a major issue. So we're interested in looking at what some of the important factors were, and we looked at refugee camps across the world. So you can see the countries where we were studying them shown in orange. So we're looking in Peru, Jordan, Turkey, Bangladesh, Djibouti, and Ethiopia. And we were looking at a range of different things that could affect the air quality. So we're looking at total VOCs, looking for particularly toxic compounds such as benzene and formaldehyde, and also looking at particulates and carbon dioxide. We were analysing particulates using a dust track, the VOCs using absorbent tubes, which were then analysed on a GCMS, and we had a portable CO2 monitor. And you can see the table, so you can see that we weren't able to use all these techniques everywhere, but for most of the camps, we were able to do some studies on particulates and VOCs. And we can see this table just shows some facts about some of the shelters. And what's particularly interesting here is to look at what cooking fuels are being used. So you can see that in Jordan, a lot of liquid petroleum gas, gas bottles were used, which tends to be a cleaner fuel. But in a lot of the camps, so in Turkey, they used some wood. In Ethiopia, they used charcoal. In Djibouti, they were using kerosene. In Bangladesh, they used a lot of wood. And then in Peru, it was a combination of gas and wood being used. These are just some pictures of some of the shelters to give you an idea of what the variation was across those different locations. So this is from the camp in Jordan. This is from Azraq and Tatari. This one is from Turkey. So you can see different. You can see the different sort of cooking environments. You can see in the top right the gas cooker there. We can see here a stove with the chimney going out through the wall, and in the bottom right again a gas hob. We can see in Ethiopia some more traditional cooking using burning solid fuel. And then in Peru we can see some of the shelters there. I haven't got a picture of the cooking there. Oh yes, we have. So here we've got some examples of cooking. So cooking using wood, and then cooking using a gas hob. And then again, these are some more pictures of an outdoor wood fire and an indoor gas hob. And in Bangladesh, we can see again burning wood inside a shelter. And in Djibouti, we can see again an example of a kerosene stove being used in an indoor environment. So what do the results look like? Well, first of all, we look at the VOCs. So we can see all the different buildings that were monitored, the shelters that were monitored, and the different locations down the left-hand side of that table. And the column for total VOCs shows relatively low concentrations for the majority of the shelters, apart from the shelters in Djibouti, which are shown highlighted. So you can see that I've blown that up, and you can see very high total VOC concentrations. And these tend to correspond to cooking with kerosene and also deep frying. So we can see that when cooking was undertaken on an electric hob, so that wouldn't produce any pollution, but when you're deep frying fish, we saw around 3,000 micrograms per meter cubed for the total VOCs. So the actual sort of cooking process can also put pollutants into the environment. If we look at the level of particulates without cooking, we see levels which are around 100 to 200 micrograms per meter squared, increasing up to 300 or 400 grams per meter, per meter cubed, not meter squared. If we look at where cooking is occurring, we can see that the levels of VOCs get, the level of particulates get very, very high. So we can see that if you look at this bar chart here, these are the results from the dust track. So we've got the PM1, 2.54 and 10 being shown. And I've put pink blocks at the top of the bar chart, which correspond to all the shelters where cooking was going on. So you can see that there's a clear correlation between cooking and very high levels of particulates in the shelter. We saw fluctuating levels of carbon dioxide, and this was particularly apparent when it was hot. So when the air conditioning was being used, people would naturally close the windows in order to stop the hot air from getting in, and then obviously closing the windows was reducing the air exchange rate and causing allowing the carbon dioxide levels to increase. So we can see that that was having effect on CO2. Some other examples of things that lead to poor air quality. So we've got some mold growth on medium density fiberboard in Jordan. So fungal spores are obviously not particularly good if you're breathing a lot of them in. There's the effect of termites and insects on bamboo. So this is an example in Bangladesh, and these termites can produce like sawdust, so fine dust, which isn't very good for you for your respiratory system, which can cause dust inside shelters. We've got an example here of a termite infestation inside a shelter in Ethiopia. And sometimes the people living in these shelters would try and poison the termites with kerosene, which of course is not particularly good in terms of putting vapors into the air, which aren't healthy. We've got some examples here again of termite infestation in Djibouti. So in conclusion, we looked at 53 individual shelters and took measurements in 424 shelters in Jordan and Ethiopia. Actually, I think that might be 42. That might be a misprint. So some of the factors impacting the air quality were culture and behavioural, location and climate. The design of the shelter was very important, including the materials used in the shelter and the way the shelter was used by its occupants. We saw very high harmful levels of pollutants, which are often related to excess mortality. Total VOC concentrations up to 102,000 micrograms per meter cubed. Particulate levels over 3,000 micrograms per meter cubed, and CO2 levels in excess of 5,000 ppm. The reasons for these high concentrations were down to a number of different sort of factors, and we found that air quality was an issue in self-built shelters and also mass manufactured shelters as well. And it was a common problem either due to VOCs or particulates across a range of climates and cultures. So some of the recommendations to improve things were improving airflow within the shelters, and this might be due to windows being blocked for a number of different reasons. And then also when cooking indoors, installing chimneys and allowing the smoke to escape properly rather than building up inside. And then in arid locations where there's a lot of dust, taking measures to reduce dust ingress into the buildings. Also in some cultures where people would smoke and also burn incense, this could lead to a reduced air quality inside the shelters. And as mentioned before, spraying kerosene as an insecticide can reduce the air quality. So I think that that's the end of the talk. So these are just some of the publications that cover what I've covered in the talk. So if anybody wants to read up, then these are all available.
Yeah. Thank you, Dr. Richard, for a wonderful talk covering both the indoor and outdoor issues, particularly focused towards the reactions and addressing some technology that may be beneficial in addressing both gaseous and particulate pollutants. I will just try to look for some questions. So there are some online questions are there. But before that, Richard, can you? We'll have some quick photo. So I'll request all of you to start your camera so that we'll have a photo, and then we'll discuss the questions, so that by the time Richard also gets some time to recoup his energy. So Saket, can you take? Sorry, Swaroop.
Sir.
Can you just make sure that everybody please start your camera?
Professor Richard, can you please unshare the slides from your side so that
Oh yes, sorry.
it's fine?
Yeah, let me.
Sachin, I'll call you back after 5
Yes.
minutes. Okay, I'll just get back to 1 minute. I'll just in the 1 minute.
Yes, sir. Taken, sir. Thank you all. Taken, sir.
Okay, have you taken?
Yes, sir. Taken, sir.
I'm sorry. Okay, so Richard, just quickly to look at it, you know, although this TiO2, all this nano particle or nanotechnology based solutions, do you think it will going to address, because air pollution is such a, you know, the amount of air pollutions coming in a short duration is a huge volume. And how do you, you know, what's your suggestion, how this nanotechnology will be beneficial in addressing this large volume of pollution, particularly in the ambient side? Of course, in the indoor environment, maybe it will be beneficial.
So you're saying for outdoor pollution?
Yes.
So one of the keys to you know, titanium dioxide and nanotechnology is the high surface area that you can achieve. So if you wanted the capacity to be able to absorb a very large volume of pollutants, then there is the potential to put a nano-structured coating on the surface of a building, which would have like a very high surface area and perhaps the capacity to absorb the level of pollutants present. But I think that outdoors, those pollutants have got to come into contact with the surface of that building to be absorbed. So if they're just being if they're just hanging in the air, then they're not going to come out of the air. I guess one of the main ways to try and reduce like pollutants and improve air quality in major cities is to reduce the things that are producing the pollutants, which is generally traffic and burning fuel and industry as well. So trying to address factors like that, I think that there is capacity to use titanium dioxide as a photocatalyst. There is work looking at the long-term effectiveness of it. So there have been studies done to look at you know, what the real life benefits are when if you were to treat a portion of a city with photocatalytic coatings. And what those initial studies have shown is that, first of all, it can be very difficult to get consistent results outside. So some studies have shown like quite a good beneficial effect, whereas other studies have shown a smaller you know, impact of the titanium dioxide. And also, if you want to do a study outside, has to be over a long enough length of time. So you would have to do it over sort of months or years. If you did a study over days or weeks, you probably wouldn't have enough data to really be able to draw a solid conclusion. So I think it's still an area which there's still scope to develop the materials to make them more effective. There's scope to look at how we optimize their performance if we are going to use them, and there's scope to study to try and get more high quality data on exactly what the benefits are.
Okay.
We can show in a lab that they work, but you know, showing how well they work outside is another thing.
Yeah, maybe we can also think about how this nano materials can be mixed with large size building. Maybe the surface area can be available, particularly large structures. The coating can be part of the building material itself. Probably it will also helpful in addressing the pollution. Am I right?
Yes. Yeah.
Yeah. Okay. So there is another question. You know, in particularly in Indian context, if you try to see in urban areas, there is not much issues with sulfur dioxide, you know, emissions. Of course, there are study shows that NOx concentrations are keep increasing, but particulates is the main issue. So how do you see that the technology, what you have looked, how do we see that it can be addressed with particulate matter, particularly the smaller size particles that is also keep increasing because of various you know, activities and reasons?
I mean, I think that dealing with particulates is a particularly difficult problem because in terms of photocatalytic coatings aren't going to have a significant effect on the particulates. And I mean, obviously a lot of particulates come from they can come from vehicles, they can come from combustion, perhaps industrial processes. We saw from the refugee camp work that in dusty environments we can have particulates. So it may be possible to reduce particulates from things like traffic, for instance, by having more efficient engines, by reducing the level of traffic. But there's still going to be particulates in some environments from sort of naturally occurring dust. And in terms of how you actually take it out of the air, I think that's a very difficult challenge to address.
Yeah. So, did you also look at it how particulates will affect on the monuments and buildings? Do you have some studies available on that?
So in terms of the effect of particulates on buildings, obviously we see that Bath stone turning black, and that's a gypsum crust. Gypsum is of course white, so the black is pollution, and it's like to be carbon particulates from exhaust from engines such as diesel engines. And also from tyres on the road. So you think about where all the tyre rubber goes when you replace your tyre, all that rubber's probably gone into the atmosphere as a lot of it as particulates. So that those can be incorporated into the surface of buildings, and also from like a historical building perspective. There are cases where you can get biological growth on the surface of buildings that can cause a problem, and some of those bacteria or algae may feed on carbon particulates, carbon pollution that's deposited. So that could be a probably less significant factor, or only significant in specific sort of situations.
Okay, yeah. This with reference to this photocatalytic reactions, do you look at it in a different phase, how the reactions enhances in removing the pollutants?
So what do you mean in a different? You mean if you do it in a liquid or a gas?
Yes, yes.
Yeah. So in terms of testing in the gas phase, that's ideal. So we as you saw from my talk, we've looked at the gas phase, the aqueous phase, and we've used dyes on the surface. Doing it in the gas phase is their standards to do it, so you can do it. It's setting up the equipment can be sort of a bit fiddly, so you have to make sure that everything is commissioned properly and it's operating properly. But I think it depends. I mean, there's a lot of interest in using titanium dioxide for water purification as well as air quality. So
Yeah.
doing tests in the aqueous environment, perhaps probably technically a bit simpler than doing it in the gas phase. And also you can sort of translate some of the results. So if something works in an aqueous environment, then it may well work in the gas phase as well. But I'm being slightly cautious when I'm saying that, because there are a number of factors that can give sort of misleading results when you're doing some of these tests, such as, for instance, if you're looking at the degradation of dye in an aqueous environment, then you may have absorption effects, and you may have absorption effects as well if you're looking at degradation in the gas phase. So things like that could complicate interpretation of results, and you need to be sort of aware and careful of those sorts of things.
Okay. Yeah. Thank you very much. So I mean, you may be aware of it. Our world famous monument Taj Mahal is not affected by particulates pollution, but there are also studies indicates that because of the water pollution in the Yamuna River might be one of the reason for affecting the Taj Mahal. So is that something which can also be addressed with TiO2 technology?
So in terms of the water and how that might affect the Taj Mahal, I mean, you've got a river, and the Taj Mahal is sort of in close proximity to the river. So certainly moisture moving through the riverbank, through the soil and into the foundations, and whether that's going into the foundations and finding its way up into the marble, could have an effect. Moisture in buildings isn't particularly good. Often it can lead to issues. I would have thought that one of the processes, I'm speculating here, but one of the processes that can lead to degradation of porous building materials is deposition of soluble salts. So if you've got pollutants in the river and also in the soil, and you've got movement of moisture, and you've got some chemical reactions which are drawing soluble salts into that marble, and then those salts are moving up through the marble, and then the moisture content is decreasing, so you get precipitation, then that could possibly cause damage. That could be inside the marble. It could well be on the outside of the marble, so there could be precipitation on the outside. If there was, in terms of, to answer your question about titanium dioxide, if you were to apply titanium dioxide to the surface of the marble, then it could degrade pollutants at the surface. If you've got things like SO2 around, then it could well catalyze the oxidation, leading to accelerating reaction on the surface. So it could possibly have a negative effect. I'm not sure. Certainly, putting a thin sacrificial coating, which is breathable, and repeated application, if it's a reversible coating, so you're not doing anything permanent, then that could be something that you could use, just to try and mitigate the effects of pollution.
Okay, so yeah, I just wanted to, I think there is one more question. For the study conducted used by anatase phase only, I wanted to know the significance behind it. Do you understand this question?
Yes. So titanium dioxide has 3 crystal forms: brookite, rutile, and anatase. And brookite is like a natural form that's sort of less common. Rutile is used extensively in TiO2 when it's used as a white pigment. So if you've got any white paint or white plastic or white materials, the chances are is that titanium dioxide is a pigment. And in fact, if you look at the absorption band of TiO2, the fact that it absorbs that UV light and the way that it absorbs it absorbs the UV, it doesn't absorb the visible light, so all that visible light gets reflected off. So it's a very, very white pigment. So we use rutile. The photocatalytic activity, so rutile is photocatalytically active. So if you have some white paint that's old, then you might notice it goes yellow. And so one of the reasons for sort of that discoloration can be because you've got photocatalytic reaction occurring, which is over a very long period of time breaking down the resin in that paint. Anatase is a much more reactive form of, or much more photocatalytically reactive form of titanium dioxide. So if you want to use titanium dioxide as a photocatalyst, then you would try and get the anatase form. So the anatase form is slightly less stable than the rutile. So if you want to manufacture titanium dioxide nanoparticles, what you do is you make them and they're amorphous, and then you would heat treat them. And if you can heat treat them at the right temperature and duration, then you want to optimize your concentration of anatase. And if you don't do it correctly, then you can convert to rutile. So you have to get your sort of heat treatment right. But that's the reason that we use anatase.
Okay. Yeah. Thanks, Richard. I think you have nicely explained many, questions which raised by the participants. So thank you very much. It was a very, a wonderful talk. Many issues you have discussed and are very relevant to the current context. And you have showed that the TiO2 can give us some kind of an advantage in addressing some of the pollutions both in urban and rural environment. I request Dr. Madhusudan to summarize the talk and propose vote of thanks.
Yeah, good afternoon, everyone. It is my privilege and duty to thank Professor Richard Ball for accepting and delivering a thought-provoking lecture today. So basically, if you look into his today's subject, it is the mitigating the effects of air pollutants on people and building. So I consider that his lecture having 3 parts. One is the historical pollution and how the restoration can take place. The second one, he touched upon the indoor air quality, and the third part of the lecture was related to air quality in refugee shelters. If you look into the first part, he explained the different materials which can be used for the restoration and mitigation measures. Basically, the calcium hydroxide, that is nanoline nanoparticles, then the titanium dioxide, and then the graphene with the titanium dioxide. So in all the three cases, he explained the preparation, how the chemical will react with the substrate materials, and how the results are giving, and these were explained through the test methods as well as the results. Coming to the next part, that is the indoor air quality issues, particularly the deterioration of indoor air quality due to airtight buildings, low exchange of rates, and the sick building syndromes. He explained how to improve the indoor air quality. That is with the comparison study of different VOCs, and the materials were explained very well. So with that, how we can improve the indoor air quality. Coming to the air quality in refugee shelters, the study of 53 such refugee shelters were explained at different parts of the world, and the tests were basically done with handheld instruments, and the results were summarized and explained. However, the results looks very alarming, stating more than 3,000 particulate matters reported in some of the shelters, quite alarming nature. And the lecture as a whole, really it is quite meaningful since our country is also looking for the restoration and mitigation of very old buildings, particularly the archaeological survey of India is looking into such aspects, and many such measures are being taken. So it is my duty, and it is again on behalf of Indian Institute of Technology Madras, AQML, and CEPHA network. I thank Professor for his wonderful talk, and also on behalf, I thank all the listeners, all the professors, particularly Dr. Jindal from Ministry of Environment and Forest, and also the colleagues from pollution control boards and research institutes. I just wanted to remind all of you that there are three more issues we are looking. That is, one is the forthcoming Indian International Conference, which is going to be held from November 29 to December 1st. All are requested to participate. And the second issue is the registration of our Air Quality Management Association. Those who have not so far registered, we request you to register the Air Quality Management Association. The third issue is very important. We have the quarterly news bulletin of CEPHA. So this quarter, ending at December 31st, we have a theme called Pro-Environmental Behavior, how to be more mindfulness for the climate change. On this subject, I invite articles from all the research students and also the scholars here. So without fail, kindly send your articles. With this, once again, I thank all the participants, and especially Professor Richard Ball and Dr. Shivanagendra for his continuous support. Thank you all.
Yeah, Richard, thank you very much. It was a wonderful, and thank you. Have a good day.
Thank you for the opportunity.
Yeah, thank you. Yeah, thank you all for joining the talk. I look forward to see you in the next talk. Thank you. Bye-bye.
Okay, bye-bye.